Today we're going to be talking about how to find the symmetric equations for the line of intersection between two planes. And in this particular problem, we've been given the equations of two planes. One is 5x minus 2y minus 2z equals 1. The equation of the other plane is 4x plus y plus z equals 6. Now, we know, based on what the problem is asking, that these two planes intersect each other in a line. All we need to do is find the equation of that line and put it in the form of symmetric equations. So in order to do that, what we're going to need is a vector in the same direction as our line and a point on the line. So let's go ahead and start with the vector. What we know is that the line of intersection between these two planes is perpendicular to the normal lines for each of these planes. And that should make sense to us because remember, the normal line for each plane is the line which is perpendicular to that plane or orthogonal to any vector in that plane. We're talking about a line of intersection of these two planes. That means it's going to be a line that lies within both of these two planes. And so if there's a line that lies within this plane, that's going to be perpendicular to its normal vector. That line also lies in this plane, and it's going to be perpendicular to the normal vector for this plane. Based on that information, what we know is that if we can find normal vectors for both of these planes, then we can take the cross product of those normal vectors, and that'll give us a vector which is perpendicular to both of the normal vectors or which is parallel to our line of intersection. So to find the normal vectors, all we do is take the coefficients on our x, y, and z terms. So here in the equation of our first plane, for example, we'll take the coefficient on our x term here, which is 5, the coefficient on our y term, which when we include the sign here is -2, and then the coefficient on our z term, which is also going to be -2. That means that our normal vector, the normal vector to this plane, is 5, -2, -2. We can do the same thing here with our second equation. When we take the coefficients, we're just going to get a normal vector of 4, 1, 1 because we take those coefficients on our x, y, and z terms. So now that we have two normal vectors, we can take their cross product. The result of the cross product will be a vector which is perpendicular or orthogonal to both of these vectors. That resulting vector, of course, will then be parallel to our line of intersection. So here's what our cross product looks like. Remember, we always do a 3x3 matrix here, and we, in the first row, put I, J, and K. And then in the second row, we take our first normal vector, so 5, -2, -2. And in the third row, we take the second normal vector, 4, 1, and 1, like this. Now we just need to break this down into its discriminant parts. Remember that we're always going to start with I here, and we're going to multiply that by the 2x2 matrix which we find outside of the row in which I is located and outside of the column in which I is located. So that means these four values here, which are outside the row and column of I. So what we do is we get -2, -2, 1, 1, and we multiply that by I. Remember also here that we're putting a positive sign in front of our I term, a negative sign in front of our J term, and a positive sign in front of our K term. We always alternate that way, and we start with a positive sign. So then we're going to say minus because we want a negative sign in front of our J term here, and we're going to multiply J by everything that's outside of J's row and column. That's going to be 5, -2, 4, and 1 multiplied by J. Then we're going to add to that everything outside of K's row and column, which is 5, -2, 4, 1, and multiply that by K. Now, in order to simplify this, remember that when we have a 2x2 matrix, we just multiply the value in the upper left-hand corner by the value in the lower right-hand corner. So -2 times 1 is a -2, and then subtract from that the product of the lower left-hand corner and the upper right-hand corner. So 1 times -2 is a -2. Multiply that by I. Then we have a minus sign here. 5 times 1 is 5. Minus 4 times -2, which is -8, multiplied by J. And then add to that 5 times 1, which is 5, minus 4 times a -2, which is a -8, multiplied by K. Here we're just simplifying. -2 minus a -2 is going to be 0, so we get 0I. 5 minus a -8 is 5 plus 8, or 13. Apply this negative sign here, and we get a -13J. Then 5 minus a -8 is 5 plus 8, which is positive 13, so plus 13K. This is going to simplify to just -13J plus 13 k, but we can also write this as just the direction numbers of the vector, the coefficients on I, j, and k, which are going to be 0, -13, 13. So this vector now is the cross product of our two normal vectors. It's a vector which is orthogonal or perpendicular to these two normal vectors here. So this vector is parallel to our line of intersection between the two planes. We have a direction for that line of intersection. Now we just need a point on the line. Well, the way that we're going to find a point on the line is by plugging 0 into both equations for z. That'll get us down to just two variables, and we'll be able to use simultaneous equations to solve for those variables, and 0 will just be the value of z in our coordinate point. So here's what that looks like when we plug in 0 for z. We'll get 5x minus 2y. Here we'd get minus 2 times 0. This term just goes away. We're left with just positive 1 on the right-hand side. Same thing here when we plug in 0 for z. That term goes away, and we have 4x plus y is equal to 6. Now we want to use simultaneous equations to solve this. One way that we can do it is by multiplying this second equation. We can multiply it through by 2. When we do that, we'll get 2y here instead of just y. Then we can add these equations together to get the y's to cancel. That'll leave us only with x's, and we can solve for x. So when we do that, the first equation stays the same. We'll get 5x minus 2y is equal to 1. The second equation we multiply through the left and right-hand side by 2. 4x times 2 is 8x. Y times 2 is plus 2y. And 6 times 2 is 12. Now what we can do is add these two equations together. So we're going to add this second equation to our first equation. 5x plus 8x is 13x. Here's where the magic happens. Negative 2y plus 2y is 0, so the y's go away. 1 plus 12 on the right-hand side is 13, so we get 13, and now notice we have an equation which only involves x. So clearly we can see here, if we divide both sides by 13, that we get x is equal to 1. Now we just need to plug this value back into one of our equations to find y. Let's go ahead and plug it into this equation here because we can get y easily by itself. If we subtract 4x from both sides, we'll get y is equal to 6 minus 4x. Now we can plug x equals 1 into this equation and get y equals 6 minus 4 times 1, which is 4. So we can see that we get y equals 2. Now we have x equals 1, y equals 2. Remember that in order to get to those values, we plugged in 0 for z, so we have 3 values that we can plug into our coordinate point. We can get the point, x is 1, so we have 1, y is 2, and remember we plugged in 0 for z to get there, so our point is 1, 2, 0. This is a point that lies on the line of intersection of the two planes. Now that we have this point and this vector here, which gives us our direction numbers, writing our symmetric equations is really easy. Here's what we do to write our symmetric equations. We take our variable, let's say x, we'll take x, we subtract from that the x value from the coordinate point. In this case, it's 1, so we subtract from that 1. Then we would divide that by the x component in our vector. In this case, that's 0. Well, we can't divide by 0, so here we'll just leave it as x minus 1, and we'll leave that alone. Let's now do the same thing for y. We'll do y minus the y value from our coordinate point, which is 2, divided by the y value here in our direction vector, so we got negative 13 there for y. Then we'll do the same thing for z. We'll get z minus the z value from our coordinate point, which is 0, divided by the z component here in our vector, which is positive 13. And these are our symmetric equations. Now here's how we want to write this. We want to set all of these equations equal to one another. When we have a direction number or a number in our vector which is equal to 0, and we have to do what we did here with this x value where we don't divide by 0, then we have to leave this equation set apart. Otherwise, if all of our direction numbers in our vector here are non-zero numbers, then we can set all three of these equations equal to one another. But in this case, because we have this direction number which is equal to 0, we have to say x minus 1 is separate, so we do x minus 1, comma, and then these two symmetric equations which can be equal to one another. And then, if at all possible, we want to simplify this equation as much as we can. We can do that here by multiplying both sides of this equation by 13, because that'll cancel our denominator. So we'll get x equals 1, comma, y minus 2 divided by a negative 1 when we multiply by 13 is equal to, our minus 0 is going to go away, we're just going to be left with z over 1 because we multiplied by 13. Now if we multiply both sides by negative 1, we can get this negative 1 over here in the denominator on the left-hand side to cancel. We'll get x equals 1, comma, y minus 2 is equal to negative z. So when we multiplied by negative 1, that canceled from the left-hand side denominator over here, and we ended up with negative z over here on the right-hand side. Now you're not always going to get your denominators to cancel like that. Very often you'll be left with some value here in the denominator, but because both of our denominators were equal to one another, except that one was negative and one was positive, we were able to multiply by that negative value, just bringing the negative sign up here and eliminating the denominators, which is a cleaner way to write these symmetric equations. And that's how you find symmetric equations for a line of intersection between two planes.